usual, we will have the presentation, and also I'll keep an eye on the chat messages. If there is any questions, we'll discuss there itself. And so please let me know if there is any problem in between. Like my voice is not clear, video is not clear. If for some people, usually due to network, it will be stopping. So in that case, please log in again, exit and log in. Okay, thank you so much. Oh, great. Padmavati ma'am says everything is fine. Okay, so as I was asked to discuss about superconductivity and spin qubits for today, right? Uh, okay, so here, uh, just a minute. Yeah. In the superconductivity, there are up to two types of materials. Under that concept, I will discuss type 1 and type 2 superconducting materials. Okay. And most important thing is that there is some temperature, critical temperature, which is very much important for high superconductivity to have. Okay. And some applications based on the superconductivity. Right. Okay. In fact, we know these things knowingly, but we will now notice and appreciate their application straight away with this session. Okay, right. So this is a plan of my session. As usual, we'll have some motivational question. Why do we study superconductivity? Okay, so here itself you can say, first of all, what is superconductivity? Superconductivity meant some conductivity without any resistance. Means I'm going to have a conducting wire. Probably you are explored by now, so we'll just have a revision. Electrical current flows without any energy loss, an ultimate conductor. Okay, everybody wants such a thing. And there is an interesting effect called a Misnar effect, where a perfect diamagnetism is shown. Like last time when I discussed diamagnetic materials which oppose any external magnetic field lines, any external magnetic field. It's like north and south will repel each other in a similar fashion. A perfect diamagnetic material would not allow any magnetic field lines to go through that material. Because of that, you know what happens? Okay, magnets are repelled. Okay, if there is a very large magnet is there, if I bring a diamagnetic material, it will oppose that magnetic field lines to go through, right? So that we will see. Okay, so that is called a Misner effect for you. And the next thing is macroscopic quantum coherence. What I mean, if I have a superconducting material, okay, if I somehow make some phase changes inside the system by reducing the temperature to very, very lower values, let's say millikelvins, you know what happens? The electrons start pairing up. Once they start pairing up, they become very, very powerful and they can travel without any resistance whatsoever. One more thing is these Cooper pairs are pairing up to microscopic entities like electrons to a distance about macroscopic distances. Okay, microscopic means atomic and subatomic level, molecular level. Anything bigger than that, you can say a macroscopic levels, distances. So that is what we see in the case of superconducting materials. So one or the other, these things are going to give us a beautiful applications for us. So that's why superconductivity is one of the most striking manifestation of quantum mechanics at macroscopic level. You see, such an interesting thing. Quantum phenomenon happens, that is anything related to quantum mechanics, right? They happen at a microscopic level, but even at a slightly macroscopic level, we will see these effects manifest, show up their nature, right? For example, in the form of superconducting Cooper pairs. Okay, right. So that is where we need to study. And further question is why a quantum technology people should study? That also we'll see, right? Okay, coming back to superconducting materials, basic properties is zero resistance, diamagnetic, that is Mishner effect, and critical parameter based on the temperature they behave. Okay, you see, I have listed systematically here. If I just draw temperature versus magnetization, magnetic field, applied magnetic field, there is a phase diagram. If I see, right, as the temperature increases, the magnetic field reduces. Okay, as we know, when the temperature increases, the system, the electrons or any charges would acquire energy. They go move very haphazardly, right? Due to that, the resistance may create and so on, and there is no possible magnetic field through those material. Okay, so a zero electrical resistance at some temperature, let's say below some threshold, we can represent zero resistance in terms of resistivity. Resistivity. You know what is resistivity? Resistivity is if I just take a resistance of any material which is equal to resistivity by L into A, where L is the length of the material and A is the cross section of that material. Let's say I have a conducting wire or any wire per se. So the area is A and length is the wire and resistivity is the material property. How much resistance per length per area it should, the resistivity would execute. Okay, all right. So key property of superconductor is the resistivity itself going to zero, rho is going to zero. Mixner effect, we just saw earlier, magnetic field through or magnetic field presence in the material is absolutely zero. Okay, which means magnetic field lines are expelled out of the expelled, may not allow to go inside the material. So I have a figure for you, I'll show you that, which is a perfect diamagnet. Okay, anything paramagnet and ferromagnet we saw last time, they will align as per the applied magnetic field. Means they are letting the applied magnetic field lines going through the material. So paramagnetic, individually there are no domains. We saw last time in the ferromagnetic there is a domains of sections where magnetic fields are already aligned in particular direction. With external magnetic field, we see arrangement of all the field lines apply as per the applied magnetic field direction. Okay, critical magnetic field. Okay, critical magnetic field is beyond certain value, superconductivity is also destroyed. So we can't have superconductivity beyond certain value. Okay, fine. Yeah, this is a figure for you to describe what is a Mishner effect. When a superconductor is cooled to a below threshold temperature in an applied magnetic field, you know what happens? The field lines of applied magnetic field are completely expelled from the material. Okay. If not, okay, then you might say there's a type 2. If it is expelled, that is a type 1 superconductor. Okay. the phase change actually happening depending on the temperature. Okay. So if I have same material inside a magnetic field, if the temperature is not appropriate, if it is more than the threshold, you know what happens? Just field lines going through the material. Okay. The moment you reduce the temperature, you know what happens? Somehow some currents are induced due to superconductivity inside a material. Because of that currents inside the material, there is a magnetic field lines are generated. They generated in such a fashion. The magnetic field lines generated by the material, the sample you say, right, exactly opposite to the applied magnetic field lines. You see, the red color ones are coming down, the red color ones are coming down, the blue ones are, sorry, the magnetic field lines are going to repel in such a way, like magnetic field lines, these two are going to repel. The magnetic field lines never cross, you see. Okay. So due to this induced current, induced magnetic field, external magnetic field gets repelled each other with the induced field. Okay. This is a Meissner effect for you. When this will switch on? Only when the temperature is below certain threshold value, critical temperature. All right. So this is a famous diagram, probably you might have seen. There is a superconducting material cube is there. Okay, you pour liquid helium and liquid nitrogen to reduce the temperature to millikelvin. If the below there is a permanent magnet is there, immediately the superconducting material will be lifted up. Okay, right? So there is a magnetic field generated by the top region. This is superconducting material would oppose the field lines of the permanent magnet which is there in the bottom. So this is called a levitation effect. Okay. Once the things get levitated, you can, if you just rotate this superconducting material, it keeps rotating continuously. In fact, this is the idea which is being used for this bullet trains, where there is above the shaft of the railing. Okay, there will be railings, right? On the railings, the train shaft will be there. The shaft will be just repelling the railings. In that, there is a small air gap is created once you switch on the uh, superconductivity. Or you can even use in such a way opposite magnetic field lines are created with the south and north pole. Sorry, it's north to north pole, like poles, and then repel, right? So railing is north pole and the shaft of the train is north pole, and they repel. That way we can make it levitate and then travel fast without any resistance. Okay, right. If you see here, this is a fundamentally different from perfect conductor. It is an actively thermodynamic state. It's just switched on only due to the temperature variation. It's a thermodynamical state. Okay. B is zero inside magnetic the material, and the susceptibility is negative. What is susceptibility for you? Last time we saw susceptibility chi is magnetization divided by applied magnetic field H. How much magnetic field is magnetized, material is being magnetized. Okay, if it is magnetized in the same applied field direction, then chi will be positive. Okay, we can't have absolutely equal magnetic field, so m and h quantity wise may not be same. M is always less than, but which direction magnetization is taking place? If it is taking place in the same direction, then the positive, that is a paramagnetic or ferromagnetic. If the M is going to be negative, magnetization is done in the opposite direction to the applied magnetic field, their chi is negative. If M and H both are equal and opposite, it is a perfect diamagnet, which is only possible, at what temperature? Critical temperature. Less than critical temperature, which is only possible to seen at using superconducting materials. Okay, so here the surface currents create this opposite field. Okay, whatever we are seeing, so So those are the surface currents triggered due to the temperature reducing to, say millikelvin, where threshold current, where superconductivity is switched on. Okay, so the London penetration depth you can calculate for this particular material based on the nature of the superconducting entity which we have chosen. It is going to talk about the magnetization, the magnetic moments, and number of charges and its density and electron charge and so on. So the factors are there. We are not going to worry too much. We are going to take the idea here. Okay. Right. Let me go further. Type 1 superconductor in detail. Okay. Right. So magnetic field is entirely expelled for temperatures less than threshold. So I have T here. T is less than Tc. Just a small correction here. Okay. And a single critical field superconductivity is destroyed after temperature above than Tc. Okay. Right. So there is a small correction. Right. And so there is abrupt first order transition. Sharp discontinuous phase transition happens, at a temperature going across Tc value. Why it is? You can see at this right side there is an equation which talks about at any given temperature what is the field. Okay, right? What is the magnetization field Hc? From there you can see that. So some of the examples, pure elemental metals, we have lead. What is the critical temperature needed for that? 7.2 Kelvin. Mercury 4.15 Kelvin, right? And tin and aluminum. So accordingly, the temperatures are there. Okay, right? Uh, so low critical fields, Hc typically less than 0.1. Okay, into T, it's unsuitable for high field magnetic applications. So we have to work in that way according to that. So the selected type 1's elements, whatever I have here written in the table. Okay, how much critical magnetization or the magnetic moments we can get is also mentioned here in millitesla. Okay, right? Okay, so let me go further. Okay, so this is a phase behavior, what we saw from normal to superconducting. Superconducting in the sense from type 1 to type 2, how the transition would take place. Okay, right? So sometimes there is a mixed state is also possible. What is a mixed state is few lines go through. Okay, earlier maximum number of lines are going through applied magnetic field lines. Later, only few lines because temperature may not be completely, entire material may not be completely below certain critical temperature. So there are some reasons where there is no superconductivity is triggered. In that case, you know what happens? Few lines are actually going through. Okay, when the entire material becomes less than critical temperature, in that case the entire material will have opposing magnetic field lines. Because of the field lines, the magnetic field would not penetrate and would see complete Misner effect. Okay, so now this is actually described by a BCS theory, which is known as Bardeen, Cooper and Schaefer's theory, where they use Cooper pairs, which are known and understood as two electrons pair via phonon mediated attraction. Okay, what is this phonon mediated attraction means? If I just take a lattice structure, the material like atoms or molecules which are connected by bond, they themselves, the nuclei, they themselves do vibrations, phonon vibrations. It's called, the electrons were put into a field distribution in such a way, right? Right. Earlier, electrons were repelling each other, and they travel on their own far from each other because of this phonon vibrations. Okay, what happens? There is some kind of a field distribution created in such way the electrons are made to travel together. Okay, it's like I can give a simple example. Let's say if I have a corridor like this. Okay, if some students were asked to go through, they'll just haphazardly go through one by one, like that. Okay. Now, sir, yeah, we don't have any system that students will go through it, or people will go through it, the corridor. But if I happen to have a corridor, something like this, there are locations where corridor is wide, there are locations where corridor is very, very thin. So wherever the corridor is wide, students, people will just go as per their wish, like that. Okay. But there are locations corridor is very thin. There we see two of them, a few of them appear to go together. Okay, somewhere exactly at a very small region, so they have to appear go together. So this is actually some kind of analogy we can use to understand the Cooper pairs. Formation of two opposite, sorry, same charged particles like electron appear to form a pair which works together and travel together. Okay. Now, so there exists the energy gap at the Fermi level between below certain threshold temperature. I think I have 1 minute. Do I have? Okay, I don't have. We have seen as the like last time the the band structure. Okay, the band structure we have seen. I think I have it in the next session where I can show you in the band structure case, especially for superconducting materials. We have like a okay, maybe yeah, superconducting materials. There exists a band gap between conduction and valency band. Between there is a Fermi level. Fermi level is the one which at least ensures that there is a possibility of jumping of electrons from valency band to conduction band. Okay, and so if the gap between Fermi level to the conduction band is too much, then there is no possibility to have any conduction. But if the temperature goes below critical value, the gap actually reduces or uh, in such a way opens up in the sense there is a possibility of jumping the free electrons through the Fermi level into the conduction band. Okay, right? So there exists a coherence length, that is the size of the Cooper pair, which is of order of few micrometers. Okay, that's what I was saying. Micrometer is very, very large compared to what is micrometer 10 to the power minus 6 compared to size of the atom or the electrons. Okay, right? Right. So there is something called Ginsburg lambda parameter, which would be used to study the surface energy, surface currents, and why the field fully expelled. Okay, as we see the complete Mr. effects being manifested. Okay, right? So we are not getting into the details of solid state physics, which is being going to be discussed in detail. What I am going to touch here is I'm just going to give you the flavor of what is type 1 and type 2 superconductors are. Okay, right? Limitations for the superconductor of type 1 is at very low TC and high IC, not practical for high field or room temperature applications. What I mean is, to have superconductivity, we need always to have a cryogenic temperatures, which means for every application, I have to cool the system to that such a lower level. So that is where for the transphone qubits, which is having integral part of Josephson junction in it, where to switch on the superconductivity, you have to pour liquid helium and liquid hydrogen to reduce the temperature to millikelvin at the chip level. Okay. Yeah. Type 2 superconductors. Okay. So yeah, we'll just study the details what we saw last time in the previous slides. Okay. Uh, there is a reasons of HC1, HC2. What is HC2? HC2 is from normal to a part of superconductivity, a part of normal, we are actually transitioning. So this is the initial level of Weistar state. Okay, that is a part of vortex states are created where magnetic field lines are there, and a part of field lines going through the material. Okay, so there is a flux penetrates in a quantized vortex tubes, means certain locations only field lines travel through, and at the same time superconductivity persists in bulk. Okay, right? So there are reasons, you see, those are the vortex. What is a vortex we'll see in the next slide. Okay, once the complete superconductivity is switched on, we'll call it as HC2 is a normal, HC1 is a complete going from top to bottom. Okay, right? Okay, so in between HC1 and HC2, we have mixed state. Okay, and below HC1, we have a very good superconducting state. Right? Okay. Yeah, this is where we see no magnetic field lines. So this would correspond to this part, and mixed state would correspond to here, and without any superconductivity is correspond to this. Okay. Yeah. Now I was talking about what is this vortex physics, no? So if you see from the side, there are locations where the field lines were allowed to travel through that. Okay, this is a side view. If you see from the top, what you see is because of the field lines going through, there are some currents are generated inside the material. See, the currents are magnetic field induces the current. Okay, the current, this is J means current density, and these are the magnetic flux, which is magnetic field multiplied by area, right? Okay. Okay, then here in a mixed state, magnetic flux penetrates as a quantized flux tubes called vortices in a particular region, and it's also called fluxons. Each vortex contains exactly one flux quantum. Okay, how many field lines going through that can be quantized in terms of some fluxons, where each fluxon or a flux quantum is represented as Planck's constant divided by He, sorry, 2E. Okay, the exact value you can see in terms of some number. Okay, now vortex structure, it's a normal core which is of the radius the psi at the center of the vortex. Okay, and circulating supercurrents of the radius lambda. Okay, and these things can exist at different locations in a triangular vortex arrangement, something of like it, whatever shown here. Okay, right? Okay, so type 2 materials and their applications. If I we realize with the niobium titanium, so the critical temperature for having a Mr. effect is 9.2 Kelvin. How much magnetization, magnetic moments we can see, critical magnetization we can see is required is 15 Tesla. Okay, to see that. And similarly, other materials also showed here. And applications, for example, for MRI scanners, okay, we will use niobium based materials. For particle accelerators, you see Large Hadron Collider, which is there. Famously, we have LHC in Switzerland. Okay, in this is a Switzerland, France, and Germany and Belgium. They all together have a Large Hadron Collider where cyclotron idea is being explored. Charges are accelerated in a magnetic field for a very larger speed, and these particles, subatomic particles, are made to collide after accelerating to a very high speed, and they break into particles, subatomic particles, and they study those subatomic particles and to see how neutrons or protons or electrons and how they're made up, why they're put together, all those things were studied at Large Hadron Colliders, where okay, magnetic field generation and is used through this kind of a superconducting materials. They can generate up to 16 Tesla. Okay. Now, like I said, trains, levitation via persistent supercurrents. So, right. So likewise, there are different materials are there. They can be used for this trains. And when it comes to quantum computers, the ones which are connected to our quantum technology is Josephson junction. Okay, for qubit fabrication. And also in squids sensors, it is being used most, as squids are more sensitive to magnetic field, so we can have a detectors out of it, the squids. And also the lossless transmission with the HTS power cables, we can do that as well, but it always needs to be reduced to the lower temperatures. Okay, right? Okay, then this is applications. And high threshold temperature superconductors. People were exploring to have high threshold superconductors, and it is started in 1986 from Muller's time, and then till 2015, people are being explored. Even like a few years back, from some of the institutes in India, they were claiming to have seen superconductivity at room temperature, but it's not proved. Only it is theoretically proposed. Okay, right? So the open question here is pairing mechanism. Conventional BCS phonon theory, okay, fails for cuprates. Okay, spin fluctuations, resonating valency band theory, and other strongly correlated mechanisms are debated. Okay, so why exactly we are not able to see at room temperatures the superconductivity is due to the spin fluctuations and the resonating valency band, like whatever valency band theory proposes, those phenomena going to play a vital role not to have superconductivity at a room temperature. That is where resistance actually creeping in. Okay, right. So let me go for that. Okay, so this is a this is a phase diagram, more of a solid state physics. We'll just skip for time being, and we'll just go to comparison and applications. Okay, right. Uh, So comparison summary, if the materials are pure type 1 superconductors like lead, mercury and tin with less than 10 Kelvin, okay, we can have good superconductivity, okay, and we can expel magnetic field, okay, and how much magnetization, the coupling GL parameter we can realize is something like this is a parameter for solid state physics. People will not go for it. Okay, and a full expulsion of the magnetic field lines, that was V is equal to 0, and limited low HCVC. How much specific number is not there here right now. How this kind of a low temperatures of few kelvins is achieved is liquid helium, which can go up to 4 Kelvin. What we needed is anything less than 10 Kelvin. On the other case, type 2 superconductors, okay, we can slightly relax the temperatures about 40 Kelvin, okay, which is something between mixedness we see. Both a part of superconductivity is there, a part of non-superconductivity is there. That is what we saw earlier, okay. Okay, partial vortex state it is called, and GL parameter is, again, you see here it is less than 1 by square root of 2, here it is more than 1 by square root of 2. Okay, so BCS theory still talks about phonon interaction. Because of phonons only the Cooper pairs are formed. Okay, right? So for higher temperatures, conventional metals, okay, even the superconducting materials you take, if the temperatures are higher, even just above 77 Kelvin, you don't see any phonon interaction coming in, so there is no Cooper pairs formation. Okay, so the formation is there in the type 2. Due to that only we will see a part of magnetic field lines going through the material. Okay, so the practical use of type 2 is, again, MRI accelerators and qubits you can create, and power cables is actually used for high temperature superconducting materials. Okay, and liquid helium is required here, just like for type 1, type 2, both are same. For high TC materials, okay, so we just need liquid nitrogen, that is enough. Okay, right. So quantum computing or quantum technology applications here is Josephson junction based transmons, qubits from the basis of Google IBM Rigetti quantum processors which operate at few millikelvin, that is 15 millikelvin. What are these? I think I have discussed several times, but for the sake of audience, I'll just repeat once again. These are simple LCR circuits: inductor, capacitor, internal resistance. Okay, so LCR. Okay, so this, if I have some kind of a power supply, okay, and I can create an oscillator of energy. Okay, so what is this oscillator of energy which oscillates between the capacitor? If I just notice, it oscillates between certain charge and non discharge state, so that can continuously oscillate. Now that is the oscillator for us, electronic oscillator. Okay, so if you replace the inductor with something called Josephson junction, that is superconductor and the insulator, everything else remains to be same. This time, if I don't need any power supply, what I simply do, I cool the system to millikelvin temperature. You know, the moment I do that such a cooling, the currents are induced, the flux Cooper pairs travel and they constitute a current. Because of that current go through the entire circuit without any supply. Okay, so because of that, you know what happens? The capacitor going to execute some transitions and oscillatory states. From there, we can realize quantum mechanical states. Okay, I can fix only particular two states to come into the picture. You know how? For example, maybe I'll use my blackboard. One minute. Okay, so if you just see, if I have an atom, it has so many orbits, you see, like that. So if I just draw a ground state, excited state, next excited state, next excited state. As you go further and further, you see orbits are going to be very, very close to each other. Okay. Now, how can I confine the considered quantum system like an atom only two states? Only these two states are considered. How can I confine that? So, just to have two state qubit system, you know what I'll do? I'll incident energy in such a way the input energy is exactly matches with the transition frequency. if this input frequency and end energy if doesn't match with this, so this second state would never come into the picture. So in that way we do select the transition states simply by choosing the right field or field energy, you can say. Okay, so with the right field energy you choose the whatever required states. This is also called selection rules theory wise. Okay, so the field incoming will dictate what are the two states to come into the picture. Similarly, I can ensure there are various possible states for capacitor can exist quantum mechanically. Only two states can be taken into consideration. By what? By making this entire setup exposed to some microwave field. Microwave field. What is the electromagnetic field? Electromagnetic field has what? It has some electric field and magnetic field oscillating inside that. So any electromagnetic wave, doesn't matter it's a microwave or any radio wave, it is going to have electric field oscillatory and also magnetic field oscillating just perpendicular to the electric field. Okay, so the black one you can say it's like electric field oscillatory E field, and the red one you can say is a magnetic field oscillatory magnetic field. So the moment I incident such field on the transmos, it starts responding. I take the oscillatory, it's the frequency with which this electromagnetic field lines are actually a exponential ikr dot minus omega t. See, there is an angular frequency which dictates with what energy this electromagnetic wave is there, how it is oscillatory, the field lines. Okay, so that will dictate how a capacitor is going to exist in only particular two mechanical states. So it's quantum mechanical states. So two quantum mechanical states would be, let's say, one is corresponding to one to ground state energy, other one correspond to excited state energy. Okay, right? Okay, so and there is a tunnel junction of two superconductors separated with insulators, exhibits AC and DC resistance junction, and critical for qubits and also squid design. Okay, even for squid design is also this is being used. And squid magnetometers, which can be used to detect a very tiny magnetic fields coming from some sources, which can go up to 10 to the power of minus 18 Tesla. So this is being used to image brain activity. Okay, and even for geology, okay, geological study, the squid magnetometers are used. They are like a probes which detects a magnetic field. So superconducting microwave resonators and transmission lines that connect qubits coherently cover chip scale distances. So inside quantum chips, the connectivity is also going to be realized using such a superconducting materials. Okay, so this is where quantum technology is going to exploit or use the type 1 and type 2 superconducting materials. So the key takeaways here: superconductivity is a macroscopic quantum state, due to Cooper pairs, which are formed due to condensation into a coherent state, which is actually called BCS, ground state. Okay, and type 1 superconductor is a single critical magnetic HC with a complete Misnar and pure effect. With the pure metals we see that. So theoretically clean but not technically useful. Okay, type 2, which is having a both combinations with a vertex formation and with a flux quantization few magnetic field lines going through the material, is a backbone for MRI technology or accelerators, that is LHC accelerators, and quantum hardware like transpons. Okay, and high temperature superconducting uh, copper dioxide planes, D-wave pairing, liquid nitrogen liquid nitrogen cooling. These things are used. This is a mechanism, still an open research problem which is being explored right now. That is high temperature superconductors. So all modern quantum processors are built on type 2 superconductors via Josephson junction qubits. Okay, fine. So that is a takeaway for you. It's more of a information. So in the next session, okay, I have a references for you. So we'll just start the next session and then we will take a break. Okay. So next session is slightly lengthy, so that's why I devote more time for the second part. Okay. Just a minute. Okay, so far no questions, so we'll go ahead. Yeah, 388 people, so we'll go ahead. Okay. So the second part I was asked to discuss is spin qubits, especially electron spin qubits, how they are manipulated. And if I have to manipulate more than one spin qubit, I would be needing two spin qubit gates and what those qubits could be that were asked to discuss. Okay. All right. Just a preamble for you. Last time when we were discussing, if there is an atom, there is a nucleus, there are outermost orbits, the valency orbit, which makes a big difference, where free electrons are there, and the electrons revolve about the nucleus with rotational dynamics. So that is going to constitute rotational spin, angular spin. At the same time, electron also rotates on its own axis. That is going to constitute, okay, just a spin due to its own rotation about its own axis. Okay, same story would also apply for the nucleus. There is also nuclear spin. Okay, so there is a spin coming from rotational dynamics, regular conventional spin due to rotating about its own axis, nuclei and electron. Okay, so as we know, any charged particle shows some dynamics, it is going to constitute a current, and from the current the magnetic field is generated. That magnetic field would be some magnetic moment. Okay, so the magnetic moment for any rotational dynamics or any spin dynamics would be simply equal to how much current they constitute, I into area in which the such dynamics are there. For example, rotational dynamics case, the area is pi r square, and current constituted is if the electron is revolving through the entire orbit, so that would be current d by, okay, dq by dt, how much time it will take to do one complete rotation, that is the time. Okay, one time period to do rotation. Okay, so this is how you can find out what is the magnetic moment for electron rotational dynamics. If you want, I can put R stands for rotational angular momentum, translational momentum, and spin momentum is just rotating its own axis. Okay, now coming back here, spin qubits. Why do I need spin qubits? As we all know, classical bits are simply realized on arranging magnetic moments in some domains. Let's say A magnetic strip is there. I can arrange all the magnetic moments in one direction. I call it as zero. Opposite direction, if I arrange, that is one for you. So that is how I use a very large regions to store one bit. On the other hand, I use a single element like an electron, either being an up spin or a down spin. Okay, since it's a quantum in nature, so small, always it will has a possibility of existing in both of them. So that is a probabilistic in nature. We can use that to realize a qubit. So spin qubit is a very good means to realize quantum memory. Okay, right. So so let's say when the electron is revolving on its own axis, about its axis. Let's say it is rotating in a anti-clockwise direction. The electron charge is negative charge is rotating in anti-clockwise. What is a current? Current is exactly opposite, which is a clockwise. Sorry, a current is electron is revolving in a clockwise. Current would be in an anti-clockwise. So if you curl your finger anti-clockwise, you will see thumb would showing the up spin. Thumb would show north pole. So basically magnetic moment is pointed upwards. Okay. So wherever the magnetic moment is pointed, it's called a north, and bottom is a south. So this is spin up system. If the electrons start revolving in a clockwise, anti-clockwise, in that case, current would be clockwise. So once the current is clockwise, so magnetic momentum would be pointing downwards. So this is a spin down spin, a spin up, spin down. Okay, so this is how single qubits using spin as being realized. Not only that, we can take two such qubits and realize superposition states of four possible memories. This is just a 0 and 1 only stores 2 bits. If I take two such electron spins, I can store bits like 0, 0, 0, 1, 1, 0, 1, 1 to four possible memories. Okay, and the question is why these things are chosen. This happen to have long coherence time. What is a long coherence time? Long coherence time means they're going to exist in that flicking state, ground and up and down for a very, very long time. Superposition state of up and down for a very, very long time. It's like if I create a pendulum oscillate for a very long time, that is a more coherent pendulum. But coherent pendulum stops rotating after some time. Okay, if it stops rotating sometime because of the damping of oscillations. But in the case of spin qubits, it's a very long coherent time, up to microseconds to milliseconds. So which would allow us to have complex gate operations on them. And moreover, these spin qubits are manifested or created out of semiconductor materials. Okay, which means the CMOS, complementary metal oxide semiconductor materials, chips or transistors, would easily get integrated with these qubits. So fabrication using standard semiconductor processors is going to be very, very compatible. Okay, a miniaturization means they're already of the size of very small atomic level or electron level. So the nanoscale footprint about 10 to 15 nanometer per qubit is a very ideal for scaling. Okay, right? So you can have many qubits by in a very small location. By the way, the size so small, obviously they require very small amount of power. So the low energy dissipation is also there. By the way, we maintain them at a very cryogenic temperature, so that is also being taken care. Yeah. So what we'll do, we'll take a quick 5 minutes break and then we'll go and discuss about electron spin fundamentals. Okay. Just freeze the PPT at this and we'll take a 5 minutes break. Okay, let's take a break for 5 minutes. Welcome back, everyone. Looks like there are no questions in the chart. Okay, so we can go ahead. Okay, so yeah, tomorrow I'm just seeing this content, what is going to be discussed. Space scaling up spin qubits and quantum error correction is for tomorrow. Interacting qubit and photons, that is for second half of the tomorrow. Okay, okay. Fine. Okay, let's come back. Just a minute. We'll start, continue. Yeah. Okay, electron spin fundamentals. Spin, if I have to represent on paper, as we see, there is up spin and there is a down spin. So in fact, we associate some quantum numbers for the upspin and the downspin, which is represented as a spin quantum number, EMS. Spin quantum, spin quantum number. So, which is just similar to the other quantum numbers, like we know that for an electron, if it is existing in lowest ground state, which is n equal to 1, the next excited state n equal to 2, and so on, right? So that is how we represent the orbit by principal quantum number n, and there is L. L stands for rotational dynamics. Spin principal quantum number, rotational angular quantum number, n, l, m, and m stands for the spin, the rotational spin quantum number. Not only rotational dynamics quantum number are the spin. Spin is actually different from rotational spin, which is comes with the s in the subscript. So likewise, for every electron where it is located in which orbit with what angular momentum it is rotating, whether it is doing a spin rotation at its own axis or not, that is represented by some numbers. Spin quantum number, like a numbers n, l, m, these are called n, l, m. Okay, fine. The spin quantum number for an electron is plus half, that is upspin. If it is minus half, we are representing a downspin electron. Means it is rotating in clockwise for a downspin, anti-clockwise, sorry, anti-clockwise for a downspin, clockwise for upspin. Okay, right? Now, if I have to do some manipulation, some changes on a quantum state of electron spin, if its electron is upspin, if I want to rotate to downspin, so it is simply like quantum state in zero state. I want to convert them into one state. What we usually do, quantum gates is X gate. X gate, which is also represented as a sigma X, Pauli X. So what is a zero gate? Zero gate is represented as 1, 0. So sigma X or X gate acting on 1, 0 will lead to 0, 1. So that is how we make the qubit flipping from up down state to up and up to down state. Okay, and there is a polymatrix Z or sigma, like sigma Z, which is a Z gate for you. What it does, it will not vary qubit from 0 to 1 or 1 to 0, but what it does, it varies the quantum state 1 from -1 kit. Basically, it adds a phase of exponential I pi to the 1 kit state. That is a downspin is going to acquire an extra phase of I exponential I pi. So that is a Z gate for you. But overall state may not appear to have different probability. Same probability is there, but the probability amplitude is slightly different from older situation. And there is a Y gate for you. What Y gate does? Y gate is an interesting gate. It's a combination of both X and Z. X does what? It flips 0 to 1. Z does what? It flips the phase of 1 to I pi, which is -1. Okay. Now, if I want to have both the actions, I can take a Y gate. What is a Y gate does? Y flips 0 to 1. At the same time, it adds a phase. Okay. So Y gate is actually 0 minus I and 0. So what is this? If I act on 0 ket, Y acting on 0, what do you get? 0 I. What is this? This is I into 1 ket. Okay. So exponential I pi by 2. What is this? I pi by 2, which is cos pi by 2 plus I sin pi by 2. So which is equal to I. Okay. So Y gate adds a phase of pi by 2 to whatever act on which it is acted. Okay. For example, if you act Y on 1 ket, what is this? This is 0 minus I 0. What is 1 ket for you? 0 1, which is going to be minus I 0, which is minus I into 1 0, which is minus I into 0 ket. Okay. What is minus I? Exponential minus I pi by 2, which is cos minus pi by 2 plus I into sine minus pi by 2. Okay. So this is going to have minus I. Minus of the sine minus of theta is minus of sine theta. So I'll get I. So here also it is acting, you can say how much phase angle is added, which is a minus pi by 2 phase angle added, or you can also say 3 pi by 2 phase angle is added to 0 ket. Y acting on 1 gives me exponential I 3 pi by 2 0 ket. See, it is flipping from 1 to 0, 0 to 1, 1 minute, 0 to 1. At the same time, it is adding some phase, pi by 2 phase and 3 pi by 2 phase on the whatever state it is acting on. So you can say it's both X and Z actions are being not exactly the same way, but the traces of Z is there and full trace of X is there with the Y operation. Okay. So these are the 3 gates, also called Pauli spin matrix gates, which we can use to manipulate the spin qubits. Okay. And there is a very good cyclic relations exist between all these 3 things. Okay. So what is the cyclic relation is the sigma x comma sigma y. If you just take a commutator bracket, what is commutator bracket is sigma x into sigma y minus sigma y into sigma x. Okay, so this is equal to I into sigma z. Okay, so that is going to give uh, 2, okay, I into sigma z, and some factors are there. For the anti-commutator also, we'll have another relation. Anti-commutator means sigma x, sigma y is sigma x, sigma y plus sigma y, sigma x. This is anti-commutator. This is a commutator for you. This is anti-commutator. Okay. So this Pauli matrices satisfy certain relations, and from there also we can do some simplifications when we do gate operations. Multiple gates together they operate. Using them we can simplify. Okay. Okay. Prahalad ji is asking how. Okay. How you can just take. Okay. What is sigma x? Sigma x is x gate. What is that? 0 1 1 0. What is sigma y? That is y gate. What is that? 0 I, 0 minus I 0. These are the gates, quantum gates, which are designed on Pauli matrices. This is a Pauli matrix. X, y, sigma x, sigma y, sigma z. What is that? Z gate. 1 0 0 minus 1. Okay. So these are Pauli matrices or Pauli gates. Now you just take x, y, you multiply. What you get? 0 1 1 0. 0 minus I 0. What is this? You just multiply, you'll get I 0 0 minus I. What is this quantity? This is I into sigma z. Okay, fine. I into sigma z. What about yx? Okay, yx, which is 0 minus I 0 0 1 1 0. Let me calculate this. Okay, so what is the first element? First element is minus I, second element is 0, third element is 0, fourth element is I. What is this one? This is minus I sigma z. Okay, now you take a difference between xy minus yx. What is this? I sigma z minus of minus I sigma z. What is this? 2I sigma z. Okay, so that is what I have here. Okay, factor of 2 missing, you can add. Okay, so this is a cyclic relation between sigma x, sigma y, and sigma z. In short, you can write x comma y is equal to 2y into z. Okay, in terms of gate operations. Okay, if you interchange, if you just say y comma x, if you just take, okay, you will get minus 2iz. Okay, even if you can check y comma z, which is going to be 2I into x. So cyclic. If you go xy, you will get z. You go yx, you get minus z. You are going reverse order. Yz is in increasing order, so you will get x. You can cross check that. Okay, right? So this is a commutator relation. What is a commutator relation? I have for you somewhere I have written. Yeah, this is a commutator relation. X comma with rectangular brackets. If I, instead of taking a separate like a subtraction, if you just take addition, this is called anti-commutator. Okay, what do I get with the anti-commutator? X comma y anti-commutator is actually 0. You know why? You see, xy is I sigma z, yx is minus I sigma z. If I sum them, I'll get 0. So that is what anti-commutator relations are. Okay, right? So this is what we have. In fact, these things are used to simplify quantum circuits. Okay. Okay. So the commutator is commutator. What is the commutativity? What is, if there is a matrix A, there is a matrix B, they commute with each other means what? AB is equal to BA. What is that? that is AB minus BA, okay, which is equal to 0. If two matrices are said to be commute, their commutator, this factor is 0. What is a commutator? Commutator is written as A comma B. This is a commutator. Commutator will tell me whether the matrices commute with each other or not. Okay, right? We don't bother about commutator, it's called anti-commutator. What is anti-commutator? Instead of having a difference, we'll add it. This is AB plus BA. This is called anti-commutator. Okay. So there is a very good cyclic relations based on anti-commutator. Commutator exists for poly gates. That is the single qubit gates. Okay. I hope Prahalad ji gets that. Okay. Now let's go further. Spin magnetic moment. Earlier we were calculating for rotational magnetic moment. You see, we calculated if anything is rotating about a nucleus, we can calculate magnetic moment based on how much current they constitute. Okay. And here, this magnetic moment is not created by rotational dynamics. It is created by spin dynamics. Okay. So that is derived as some G factor. Okay. So which is close to 2 for free electrons. And there is a Bohr magneton for electron or nuclei which is rotating some value. It's a constant value. And a spin angular momentum. Okay. The spin value S is for half, plus half or a minus half for electron. Similarly, you can have different values for spin. Okay. So this is the overall spin magnetic moment. Spin value either integer or like a spin values are usually integers or fractions. Okay. So if the spin values are fractions, we have called fermions. The spin values are integers. They are called bosons. Okay. For example, photons have spin, integer spin. So they are called bosons. So here we are talking about electrons. They have a spin of half. The integer are fractions. Okay. So next here, key properties for spin, electron spin is their non-classical intrinsic degree of freedom. Non-classical in the sense they come at a quantum level. Okay, it's a one of the degree of freedom. Just like somebody is moving in straight line, right or left or top or bottom, at the same time they are also spinning. Or let's say not humans, let's say take a cricket ball. The first bowler just spin this bowls. Okay, if we give a spin to the ball, right, rotations, in that case, you know what happens? Ball also swings, deviate from its actual path because of the spin dynamics. Okay, and these obey Fermi-Dirac statistics. Okay, so the study of such elements which has fractional spins are described by the Fermi-Dirac statistics. It's a statistical physics terminology and the concept. Like I just said, bosons like photons, they are actually described by boson statistics. Okay, so we are not getting into the detail. This is a property or a description. You can take it for information. Okay, so spin angular momentum, how it is calculated. Okay, just like spin magnetic moment, there is a spin angular momentum is calculated with having a spin value s, multiply the square root of s into s plus 1 multiplied by Planck's constant, which comes out to be, for example, for electron, it comes out to be square root of 3 by 2 multiplied by Planck's constant, that is the spin angular momentum. Okay, right? By the way, what is the angular momentum? Angular momentum is R cross P, linear momentum. If something is rotating about some center with a radius R, if the linear momentum is P, okay, what is the angular momentum? Angular momentum is radius. You curl your finger from radius direction to the linear momentum, you get a perpendicular direction. So angular momentum is coming outwards. Okay, just like bicycle wheel standing perfectly vertical because of its rotation. Okay. Okay, then let's go further. Okay, then how do I represent this qubits, spin qubits? Like any conventional qubit, how do we represent geometrically? We take a three-dimensional polar coordinate system and we'll represent that. Okay. Uh, yeah. How do you represent? You convert alpha as cos theta by 2, beta as exponential I phi, sine theta by 2. Where theta is a polar angle, see this is a polar angle. Phi is a equatorial or azimuthal angle. So this is a polar coordinate system where three dimensions are there for a polar coordinate system. Okay, so this is a three-dimensional Cartesian coordinate system I, J, K. Okay, if I just take a sphere, if somebody moves in straight line, Cartesian coordinate system is enough for me to describe. But if somebody moves in space in a curved manner, in that case, you know what I have to do? I have to come up with a curvilinear coordinate system, which is a polar coordinate system. Let's say somebody at some point in space, if he makes a radius r, okay, that radius r makes an angle theta with what? Z axis. So this is a polar angle. Okay, with respect to pole, where this radius is making an angle. Now you drop a light from the top, this vector will create a shadow on the equatorial I and J plane, so which makes an angle phi. This is a azimuthal angle. Okay. Now you see how many coordinates are there here? R cap, theta cap, phi cap. Just like I cap, J cap, and K cap. But our qubit is two-dimensional. Moreover, the quantum state is of length 1. So you can take a unit sphere on the surface of a sphere. You can disregard the radial dimension, because unit sphere has fixed length 1. Our quantum state length is 1. Okay, so there is no need to have a radial direction, a radial dimension. So on any given point you have theta and phi value. Those things are enough for me to describe a quantum state. Okay, just like we are standing on a surface of a sphere where longitude and latitude, the location given by Google Map, Google Map gives two numbers for our location. Basically, that is theta and phi. Where exactly our location is making a vector, position vector with the center of the Earth. Okay, from the pole, North Pole. This is the North Pole. From the North Pole, there is a vector from center to North Pole. That vector and our position vector makes an angle. So that is called polar angle or a pole. Okay, so our position vector makes an angle with the pole vector. So that's why it's called polar angle. And our vector, position vector, makes a shadow on the equatorial plane. What is equatorial plane? You just chop this sphere at the exactly middle, you get an equatorial plane, equator. Okay, so on the equator, there is a shadow created. That shadow makes an angle phi with the x-axis. So that is a azimuthal angle or equatorial angle. Okay. Now people use that strategy and take cos theta by 2 as alpha, exponential I phi, sine theta by 2 as beta. So my quantum state really is what? Alpha 0 plus beta 1. Now it becomes what? It becomes cos theta by 2 0 ket, sine theta by 2 exponential I phi 1 ket. If you just take theta is 0 means you are standing exactly on the North Pole. If you stand exactly on the North Pole means what? Your theta is on North Pole. Your theta is 0, which implies what? Cos theta by 2 is 1, which implies alpha is equal to 1. What about sin theta by 2, which is 0, which implies beta is equal to 0. So therefore, my quantum state is 0 ket. So on the North Pole, the quantum state is pointed, like sitting, that is called a ground state qubit. Or you can say spin up quantum state. Electron spin is upwards. Okay, if the electron spin is downwards, pointing towards the South Pole, means what is the polar angle in that case? Polar angle will be theta equal to pi. What it implies? Cos theta by 2 is actually -1. Sorry, cos theta by 2 is a 0. Okay, which implies alpha is equal to 0. What about sin theta by 2? Sin theta by 2 is 1, which implies what? Beta is equal to exponential I phi into 1. By the way, when you have theta is equal to phi, angle pi, means you are standing on a single point. There is no shadow to be created on a single point. So the angle of phi, the phi value no more valid. So you can simply say beta is equal to 1, which implies quantum state is simply 1. This is a ground state or downspin qubit. So you can represent the South Pole as a downspin or 1 ket. Any other point you see other than North and South Pole, you will have a combination of both. So that is where you see superposition states. Okay. So that is how use a Bloch-Spear you can represent your spin qubit state geometrically. Okay. Right. I have that description. Now, how do you realize spin qubits? Okay. Spin qubits are realized you take a semiconductor materials like gallium arsenide, silicon or silicon germanium or indium arsenide. You electrostatically, you create some locations where electrons can be confined. Means electrons are made to locate, not to move anywhere. So it's just like if you create opposite charge for the electron, electrons just repel. On every direction you create such opposite charges, you know what happens? Electrons were confined to locate into that region. Okay, there is a question here. Parivartanji is asking, did not get why beta becomes 1 for theta equal to pi. Okay, let's go back. Okay, why beta becomes 1 for theta equal to pi. So theta equal to pi, this is a value. Okay, what is beta for you? What is beta? Beta is exponential I pi sine theta by 2. Okay, when theta is equal to pi, sine pi by 2 is equal to 1. So this is equal to exponential I pi into 1. So exponential I pi is there. Beta is exponential I pi. Moreover, okay, what is the quantum state? Quantum state is alpha 0 plus beta 1. By the way, for theta equal to pi, we already got cos theta by 2 is 0, alpha is equal to 0. Means what? 0 into 0 ket plus exponential I phi into 1 ket, which is simply exponential I phi into 1 ket. Okay, my quantum state is pointed along the ground state. So down, South Pole. Okay, down South Pole. But phase angle is there, some relative phase, exponential, some phase is there, exponential I phi is there. Please remember, this is single state, single bit state. Okay, single bit state, the phase is not going to matter. Because if you just take a probability amplitude and then probability, what is the probability? Probability is a norm, absolute square. What is this? absolute square. So what is the exponential I phi? What is absolute value? Exponential absolute value is cos square phi plus sine square phi, which is equal to 1 by y. Okay. So this is going to not to contribute any value. Moreover, if you just see geometrical interpretation, when you are just standing on the south pole, okay, a single point is there. On the single point, there is no notion of equatorial angle or azimuthal angle. To have an angle, such an angle, you need to have a disk, some space of disk. But on a single point, such a disk is not there. So the notion of phi, okay, is disregarded. You can simply disregard. You can simply say you can beta equal to 1. Okay, right. So can gallium nitride be used for quantum materials? Where can be application? Okay, so I explicitly, I don't have a comment on this, but gallium arsenide, if you just to take, okay, it's a semiconductor material. Inside a semiconductor material, you can create a reasons where the potential is in such a way the electrons are confined in that region. By the way, what is potential? Potential is very simple. I'll explain. If I have a well like this, okay, something falls into the hill, a well, okay. If that thing which is fallen in, if has a capability to climb up or take the energy to climb up and go out, in that case, this well doesn't matter for this, whatever is fallen in. But if that doesn't have energy, in that case, you know what happens? Whatever fallen in is confined into the well. So this is actually called potential well. Why it is called potential well? I'll create an infinite potential energy on the either side. So to climb up, this particle should take that infinite potential energy and go out. So this is a potential well for you. Okay, means the particle is only has a possibility of going left and right. That's all. It cannot go out of the material. So this is how I'm confining my particle between x is equal to 0 to x is equal to L. This much length, one-dimensional potential well. It can't go up and down. Okay, there's something like that. I have a potential hill. Potential hill. What is this is? There is a particle. If the hill height is so much, if I have infinite potential, particle never able to climb up and go to the other side. This is a classical picture for you. When you go at a quantum level, interestingly, even when the potential is infinity, there is a possibility of particle going into other side and existing there. Okay, because of its quantum nature, because of that, you know what happens? There exists a wave for this such particle. That wave would exist even in the infinite range, infinite region, but it's not that extensively with the same amplitude the wave would exist, but it's a smaller amplitude, probably diminishes. Okay, after exiting, it sustains on the other side. So there is a non-zero presence of the particle on the infinite potential and even other side of the potential. Okay, so this is what potential hill, potential well is. Why these things are required? These things are required. If I want to confine a particle to a certain region, I'll create the infinite potential on the either side. Okay, to maximally confine. So what you will do? Let's say I have an electron. I take a positive, negative plate on the right. I take one more negative plate on the left. You know what happens? Electrons were repelled on both sides due to both the plates. So electron cannot move on the left or right. I'll have one more negative plate on the top. Okay. You know what happens in this case? Electron is repelled on top and bottom. So on the all the 360 directions, I create of repulsion on the electron. In this way, what I'll do, I'll confine the electron to very small region. Not only one electron, I create many such electrons confined to the small region. This is how we can create a quantum dot having certain amount of electrons confined to a small region. Okay, now you see, literally I am telling you to put some charged plates on all the directions of the electron, which is not possible easily. So what we'll do, we'll take a semiconductor materials. Inside the semiconductor materials there are electrons and holes prepared, right? So we can take the electrons confined to certain region in such a way the electrons never move into any direction. They just clubbed at one location. So that is what a quantum dot for you. Okay, just a minute. Yeah. So that is a quantum dot inside a semiconductor material. Okay, so how it is done? We take some donors like pentavalent phosphorus donors and you dope them, and the extra electrons, pentavalent means extra. See, usually the silicon requires 4 valence electrons to share and create a bond, but we give 5 using phosphorus donors. In this way, one extra electron is lingering around in the material. We can make that electron to locate at some fix at some location. Okay, quantum dots, how it will change state. Okay, good question. Now a confined electrons into some region is going to exist in different quantum mechanical states, just like an electron existing in various states inside an atom. Let's say ground state, excited, and second excited, and so on. In a similar way, this trapped electrons going to execute multiple quantum mechanical states. From those quantum mechanical states we can extract or we can select particular 2 levels. So in that way we can realize a qubit out of a quantum dot. We'll see, I'll show you a figure in the next slide. Okay, right? The way we are just doping a silicon with the pentavalent donors like a phosphorus to create a quantum dots, we take a diamond which is made up of carbon like a 12C carbon and remove the few carbons and put nitrogen into it and leave deliberately some locations of carbon vacant spaces. This is called vacancies. In this way, a doped nitrogen, let's say usually we have carbon, right? Nicely structured carbons. Okay, let's say like this, it is there. We remove a carbon and put nitrogen there, and you leave the vacant part as it is without replacing. So you are forming nitrogen vacancy dipole. So this NV dipole is going to execute quantum mechanical states just like ground and excited and so on. We can choose only 2 particular states and you can realize a qubit out of it. So here it is called diamond impurities. Like in the diamond we can create nitrogen and then dope with the nitrogen and create a NV centers. Okay, so this is also a spin qubit, one of the quantum qubit for you, right? And also there is something called semiconductor heterostructures. Like take a combinations of semiconductors and you can create a 2D electron gas and whole spin qubits which are going to emerge with a strong spin orbit coupling. Okay, right? So there is a rotational dynamics and also spin dynamics are going to couple and then it's going to create semiconductor heterostructures. So which is a very good CMOS FET integration. Okay, so these are the various physical realizations of the spin qubits. Now coming back to question somebody was asking, how quantum dots, how they will change their state. Okay, if I just take a semiconductor material, we'll have a valency band and a conduction band. There is a band gap. Okay, right? Many atoms are there. Their all states are going to be slightly deviated from their actual state because of mutual effect on each other. So we'll have a continuous band. So this is a continuous band for you, conduction, valency and conduction band. Okay. Now, if I can manipulate their band structure by doping and so on, what we can do, we can confine certain amount of electrons within certain region. They are going to have a band structure in such a way. Individual electrons are going to have individual levels. They are going to have a valency band and a conduction band together in such a way. The band gap is in such a way, so that is going to constitute certain size and dimensions. Okay, within how much region these things are confined is going to decide what is their overall average ground state, what is their overall excited state. So only the light correspond, any light correspond to that frequency is only observed. So the electrons in the ground state of such quantum dot excite and de-excite. When they de-excite, they limit the light. For example, the energy separation is very small in this particular case, so this will respond to only low energy light, which is red color. Okay, if you have a separate longer separation, okay, more energy gap, okay, more energy gap, in this case it will respond to little higher energy light, so they absorb green light, and when they de-excite, they emit green light, and so on. If you separate and if you prepare the quantum dots in such a way, they confine to a very large region. Very large region in the sense the size wise is more, sorry, very small region, decreasing size, you see. I'm sorry, decreasing in size means lot of energy is required to excite them, and okay, which is correspond to blue light. So the light is energy is increased. So quantum dot, like electrons in the quantum dots excite to a very large high level and then de-excite, they emit this blue light. So the question is how they change their state. Okay, it is simply like any electron from ground state to excited state. They, when I supply a photon which is having exactly energy separation, they excite and then de-excite. When they de-excite, they emit the light. But even if I take in similar kind of electrons confined to small region, their ground state and excited state are not going to be equal. They're slightly deviated. Because of the slightly deviated, there is a band of states are going to have correspond to each one of them. Like each one electron would have a ground state like this. Another electron slightly deviated. Likewise, there is a bunch, right? Some of them may coincide, but not. The coinciding is here. Okay, so each electron ground state is there. Likewise, let's say 1,000 electrons are there. The 1,000 electrons have different states. Out of 1,000, let's say some 4 to 500 are overlapping. This overlapping is somewhere here. Same story for their excited states. Okay, so why they exist? Basically, electron can exist in two or many quantum mechanical states. Only two of them are shown here. Let's say this is correspond to ground, this is correspond to excited. And what happens to other 2, 3, 4 on? I'm not going to consider them because my confinement is in such a way, this atoms electrons are going to only respond to particular level, particular energy, so that energy is correspond to the energy band gap of 0 to 1. Okay, so this is how the quantum dots are prepared. Depending on the size, you get a different color. If the quantum dots are confined to very small region, they respond to very high energy. If they're confined to very large size, they respond to low energy light, that is a red light. Okay, okay, there is a question here. Any potential are potential well or hill are similar or tunneling phenomena? So yeah, they both are actually representing the tunneling phenomena, what you were mentioning. They're actually conveying the idea of the difference between classical to quantum rays. In a classical case, if there is somebody falls into well, they cannot, if there's somebody come, some other third person comes and helps, then only they can come out. Otherwise, they're stuck inside. But in a similar fashion, if I do the same experiment at quantum level, if I put an electron inside a well, okay, so we usually think classically, as per our intuition, electron can never go into the infinite region. This is the infinite region, means region 1, region 2, region 3. If the electron is put in region 2, Okay, as per our intuition, we think that electron may not go into level 1 and level 3. But quantum mechanically, you solve this problem using Schrodinger equation, that is equations of motion dynamics, and you will find there is a possible presence of electron on region 3 and region 1. Non-zero probability is there. So this will tell me that the tunneling process of electron into regions where it is not supposed to go classically. Okay, quantum mechanically it is true. Okay, even if you perform the experiment, you see that if you have such regions, you perform a measurement of electron in all the three regions. Let's say you make 1,000 observations. Out of, let's say, a few 50 times it will you see on region 1, 50 times you see on region 3, probably 950 times you see in the region 2. Okay, so when you see the comparison, region 1 and region 3 is more or less negligible to region 2, but there is a presence of electron on the infinite potential side. So the tunneling process is shown even here. Okay, the potential Hill case also, electron travels onto the other side and makes its presence seen on the other side. So this is a tunneling process. Yes, answer to your question, Keshav Ji, is both of them are actually emphasizing the process of tunneling of quantum particles. Okay, Himanshu Ji is asking, if we confine electron in 4 walls of negative electrodes, can't it tunnel through them? Oh, very good question, a counter question. It's amazing. Yes, it can tunnel through, but what anybody can do is, we see here 950 times it is confined, right? So you can choose the states which are exist only in the 950 possible probability states. We will not confine to go to 50 and 50. So in this way, you create confinement in such a way, within the confinement, what are the quantum mechanically possible two states we consider? Only two states. There are other states which system can go into other states, means tunnel out of the states. So we are not going to have a consideration in it. How? We are going to send a light through the system. That light is only going to interact. Our like a quantum dots are going to only respond to that state. How do I confine? This is how I choose my band gap separation suitable for only particular level or particular states. So in this way, we can select the system not to go out of my range. Okay, right? So that's why confining into the 4 levels, if you just use your intention, may not be sufficient to understand. But inside a semiconductor material, every direction there is a semiconductor materials there. There is a vacant space we create. Within that vacant space, we confine the electron. At a microscopic level, we are confining it, not at a macroscopic level like a potentials. Okay, all right. Okay, then let's go ahead. This is a quantum dot. Now, okay, if there is a electron state like ground and excited, let's say ground state is there and excited state, electron levels are not going to be fixed. Okay, if they have external magnetic field or electric field is applied, you know what happens? Every level gets split into two possible levels or many levels, not just two or three or four, many. Why? Because if there is an electron in that state, it is going to respond to the applied magnetic field by what? By creating its own spin magnetic moment. Okay. Earlier it is keeping quiet. The moment external magnetic field comes, it starts spinning on its own axis. And in which direction it spins, we don't know. It can spin down or up. How do you show that? By creating two more orbits about the actual orbit. So this is called a spinning. This is splitting of. Okay, so please splitting of, this is called splitting of given state in presence of the external magnetic field. If this is called Zeeman, if you use a magnetic electric field, electron level can be split into two possibles. That is called a a Larmor splitting, Zeeman and the Larmor electric field splitting the given state. Okay, so basically it is just like in a common layman terms, if you give a chocolate to somebody, a kid, he will eat and he can possibly make it excited, happy. Or if he doesn't like chocolate, he will feel sad. He wants something else. So his level may be down. So those are the possibilities. Likewise, external magnetic field is there that can put the electron probably in a spin down or a spin up state. Both are spin states, but both two possible states. So this is a Zeeman splitting. This is how we can create a qubit by external magnetic field. Okay. So the moment you switch on external magnetic field, actual magnetic spin is created in an electron with a coupling dictates how much external magnetic field and external magnetic field and the electron a given system couples, and what is the corresponding spin magnetic spin moment, a spin quantum number is that. So whether it is half or 3 by 2 or so on, that is there, and using that you can define the entire system, the Hamiltonian. Okay, having the Hamiltonian, you can just see how system evolve in time and respond to the external magnetic field, and that is all dynamics of the system. Okay, right? I can give a simple analogy here. If I have a very large bar magnet, let's say north and south. Let's say I have a compass, small compass, north and south. Once, if they are far, let's say their field lines are confined like this. Okay, they're far. So there is no interaction. Let's say that I bring the negative charge, a large magnet towards the small bar magnet. Okay, or compass. You know what happens? Compass is a very small quantity. It aligns, changes its orientation by what? Okay, if the compass is initially in this direction, north and south, once you bring the huge magnet towards it, you know what happens? It repels the north pole. So you know what happens? Alignment takes place. So it gets aligned like this. Okay. So south pole is attracted of the compass and north pole is repelled. So you will see alignment. Okay. So this is actually called precessing or rotating the small magnet as per the external magnet. Okay. So, but this is a classical picture. But in the quantum level, you know what happens? Electron, by the way, either it exists downspin or upspin. So when you have external magnetic field coming, I'll not have such a huge magnet. I'll have electromagnetic wave with some electric field and magnetic field pulsing on its own, rotating on its own. In that case, you know what happens? The external magnetic field can make the spinning of the electron continuously, like up and down, it can spin. So basically, it's like a tossing a coin. You toss a coin, make the coin to be in both the states. In a similar fashion, you can make the spin of an electron to rotate as per the applied magnetic field. It's like it is called electron spin resonance. Okay, so it is rotating external magnetic field frequency. Okay, so if the applied frequency is f, okay, so it is going to have the applied field have energy hf. How much rotation it is going to create? It is going to create a rotation in such a way. Okay, so there is a mathematical condition for resonance. From there you can figure out with what frequency it is oscillating spin system for applied field. Okay, so even in that way you can have a single qubit NOT operation or pulsing operation. Okay, what is this pulsing operation? Let's say initially my quantum state is pointed out towards the north pole. Now it has to rotate towards the x-axis, that is in this direction. Once it goes to in this direction, you know what happens? The quantum state is going to have equi superposition state. 50% ground, 50% excited. How much angle I should rotate? Pi by 2 angle I should rotate. So there is something called pi by 2 pulse is applied for a qubit or a quantum state in a zero state to become superposition state. This is a pi by 2 pulse for you. Okay. So that is called Hadamard gate. Pi by 2 pulse is a Hadamard rotation. And if I have a north pole, I want to rotate to the south pole. Okay, so let me show you with other color. If I have to rotate to the south pole, how much angle I should rotate? Pi angle. So I'll use a pi pulse to rotate from 0 to 1. So that is a X gate operation for you. So this is how single qubits are created with the gate rotations are created. Okay. So there is a arbitrary rotations also possible. Okay. What we do? You take any pulse duration, sorry, pulse area, anything other than pi by 2 or pi, what it happen? It will be here, arbitrary location, or it will be here, arbitrary location. So in that way, I can have arbitrary alpha and beta values. So basically, you are playing with the pulse area. What is the pulse area? If I have a pulse, it is going to have certain amount of area. So this area is pi by 2 value. If you integrate the area under the pulse or the area under the envelope of the pulse, it is going to have pi by 2 or pi value. Okay, there is a question here. Which parameter confirms whether an electron is confined or not in 3 dimensions in a quantum dot? Bohr exciton, radius, or de Broglie wave? Okay, yeah, it's a good question what you asked. The confinement. Okay, so let me go Zeeman splitting. Do I have an equation for you to describe that? I don't have for you here. Which value? See, Bohr magneton is a fixed value. I don't have a control. Okay, right? So what I have control? B is applied field and SZ. Okay, SZ is the thing which is actually coming out of a possible splitting or a possible spin values. Okay, right? So here, S value, SZ value in this case is a plus half or a minus half. Okay, what is MS? MS, yeah, plus half or a minus half, SZ value. So likewise, whether the system is confined to a location, it is going to have that quantumness of superposition state or not is dictated by what is a coupling parameter, how much electron has coupled to the external magnetic field, okay, and how much it is spinning on its own axis, magnetic moment, how much magnetic moment is created. Magnetic moment is actually created by external magnetic field, okay. So for a fixed B, sir, a fixed mu is being created. Okay, that is all also connected to, like, dictated by how much coupling they can be. Coupling in the sense they should match. Okay, so in a way, answer to your question is the first external magnetic field is the one which dictates the possibility, and then the response comes from the coupling and response comes from the electron. Okay, right? So it's not that easy to point out which factor would confirm whether there is a confinement or not. Okay, whether confined or not, what you can see, you can incident a light on the confinement. Whether I see some fluorescence, like a color, some light is incident, some light is emitted. From there, I can judge whether the confinement taken place or not. Okay, so the de Broglie wave would not come here. De Broglie wave is by default is there. What is the de Broglie wave? Whenever quantumness is there, quantum systems are very small and they move with a very good velocity, and there is a wavelength associated with that system, measurable wavelength, then we can talk about de Broglie wave. Here there is no question about measuring possibility or not, because they are already quantum. So de Broglie wave do exist. So that may not dictate whether the system is confined or not. Okay, right? Okay, then discuss in anti-clock. If you rotate in clockwise, then how Hadamard and X gate will be. Oh yeah, you are saying. See, this is an anti-clockwise rotation. If I rotate in the other direction, okay. Please see, rotations are always fixed. Either you take a reference, from that reference you take a clockwise or anti-clockwise. You fixed in that direction. Okay. So you usually rotate in a clockwise direction, so anti-clockwise from x-axis on the equatorial plane. If we have equatorial plane, in the x-axis we rotate from 0 x-axis to x to, okay, 0 to 2 pi. Okay. If you want to rotate in the opposite direction, which is like let's say pi by 2 I am rotating. Okay, let's have separate diagram. Okay, the initially system is in 0. If I rotate anti-clockwise, pi by 2. From 0, if I have to go to this state, I have to rotate by pi by 2. If I rotate by clockwise, that is the 3 pi by 2. Okay. So 3 pi by 2, let me draw the different color. Okay. That is 3 pi by 2. Okay. So usually I refer my rotations in the form of the pulse area. Okay. So this certain pulse having a area of pi by 2 able to create a rotation like this. You can call it as equivalent to some pulse area with the 3 pi by 2 value, but of different nature, but it rotates in the opposite direction from right side. Okay, clockwise. Fine. Okay, then X gate. In the X gate case, more or less it is the same, whether it is a clockwise or anti-clockwise, because it is going from 0 to 1. Okay, so reference book in solid state physics I have in my PPT. You can go through. Okay, then let me go further. Electrons complete. Okay, this is what an electron going up spin and down spin. It's like a oscillation. So these are called Rabi oscillations. Okay, right? So how much frequency, like what is with what frequency they're oscillating, that is dictated by incident field frequency. So incident field, magnetic field itself carries some frequency of oscillation that will dictate with what amplitude things will, okay, with what frequency things are going to oscillate. Okay, these are single qubit gates written again. Apart from inside, there is a phase gate. Okay, what is a phase gate? Phase gate is 100 exponential I some phase angle, any angle. Okay, right? Okay, so there is a Hadamard gate, that is also single qubit gate, which puts the things from 0 to superposition. And there is a T gate. What is a T gate? T gate is actually square root of Z gate. Whatever is a Z gate, you take a square root of it, you will get a T gate. Okay, spin decoherence and relaxation. So whenever I create a superposition of spin, like up spin and down spin, like a rotating, this is not going to exist of rotation forever. It is going to decay or deviate from oscillation to damping. So this is also called the decoherence factor. Okay, so that is what the relaxation is. This happens because the lifetime of upspin is going to relax, or the oscillation is going to relax. It's like a pendulum. If I give a large amplitude, I have a longer oscillations. If I give a small amplitude, it's lesser oscillations. At the same time, If I do the oscillations in the air, I'll get a long time oscillations. If I do the same experiment in water, I'll get a less amount of oscillations. So that is what the quick damping. It can happen from the lifetime of excitation, or it can happen from lifetime of oscillations itself. So those are actually referred as T1 and T2 relaxation time and coherence times. Okay. So by nature, the spin qubits are known for longer coherent times, but you can improve further by using several techniques. So I'm not going to discuss all of them. I'll skip it because we are already crossing 10 minutes. Okay. So you can create quantum applications like quantum entanglement and so on. And especially scalability is very good with the spin qubits because they are integrable with the CMOS or chips. Okay, there are applications discussed here. Okay, you can go through it. Okay, future directions, what we can see in next 10 to 15 years, that is also mentioned here. Okay, so there are some takeaways, summary and takeaways about this. Okay, so the books, somebody was asking what are the books. I have a reference books here and reference papers. You can just check them out. Okay, so that's about it for my end. So thank you very much. I did discuss all the questions, whatever is being asked. I will, for solid state physics, there is a book called QT-10. You please check that. Okay, I do put it on my other PPT. It is there, but solid state physics by QT-10 is very good book. Purely discusses solid state physics, no quantum technology or anything. Only if you want to understand why Cooper pairs and all these things are created, you will see in that book. Okay, how skyrmion would act as a qubit? Okay, I see this question was asked even in the yesterday's session. Yeah, see, anything, if it can exist in multi-quantum mechanical states, it is going to a potential mean for me to realize a qubit. Okay, anything quantum means it is not certain, not fixed in a particular location, it can particular state, it is going to exist in multiple states. Among the possible multiple states, I pick two states by selection. With whatever energy I'm going to talk, only with that energy it will respond. In that way, we realize a qubit out of it. So doesn't matter whether it's a skyrmion or doesn't matter whether it's a quantum dot or anything. Does it has a possibility to exist in multiple states? That's the first question. Yes, it does have. So in that way, we pick a particular two states by incidenting, by talking to it in a particular energy, by particular energy source. Okay. Okay. References for quantum circuits. Yeah, best reference you can start for quantum circuit is this book, Nielsen and Shuang. Okay. Right. So let me stop. I think we are meeting tomorrow as well. Like I said, tomorrow how gates would be realized if skyrmions are used. I think I am not sure about exactly how gates can be realized. So in general, I can tell. Okay, right. But the solid state physics experts who are working in quantum computing, they may be able to answer it in a right way. So if you look at the schedule, you can hold on your question and wait for uh, some other person who is going to talk about that. Okay, so exactly how gates are realized for skyrmion, I am not the right person. I don't have the background to answer it. Okay. Okay then. So looking at the schedule, I have next session is about scaling up spin qubits and quantum error correction with respect to that, and interfacing qubit and photons. So that is for tomorrow. So let's meet tomorrow and we'll discuss little bit more in detail. And for your question, I think uh, regarding skirmion, Niti ji, let me check myself and I'll come back to you on that tomorrow. Okay, thank you.
Thank you so much, sir, for this wonderful session. And I request you, sir, to kindly share this PPT on the FDP email ID so that participants can get the study material.
Ma'am, can I do one thing? I think last time I sent to whom? Deepesh ji, I sent
Yes.
yesterday. I'll send
Okay.
again.
Okay, on
Uh,
same ID you can send,
yeah,
sir.
yeah. I'm sending
And
both my PPTs to Deepesh ji for he can
okay,
put it
okay,
up.
sir.
Yeah.
Okay, thank you, sir. And on behalf of EICT Academy and MNIT Jaipur, I express my gratitude to you, sir. And there's a one more announcement for all the participants that quiz second of QT-10 will be available today from 6 p.m. till 24th May, Sunday, 11:59 p.m. So I request all the participants to attempt the quiz with their respected registered ID, and those participants who have not attempted quiz 1 earlier, the link for quiz 1 is also available, so they can attempt today till till 24th May 11:59 p.m. the same timing for both the quizzes, so they can attempt. If they have any query, they can mail it or you can ask here only regarding quizzes. Okay, participants, if you don't have any doubt, then we can end this webinar or this session. Thank you so much.